Hello students, now here let's see types of diagrams or the directed graphs. So first, simple digraph. A digraph that has no self loop or parallel edges is called a simple digraph. It is directed graph but without self loop and parallel edges. Okay. Second, symmetric digraph. A digraph in which for every edge UV there is an edge VU is called a symmetric digraph. Here, suppose V1, V2, V3. Look at it. This is in this direction, then there will be in this direction also. In reverse direction also there will be an edge. Then this is an example of symmetric graph. Third, asymmetric digraph. A digraph that has almost one directed edge, between a pair of vertices with may or may not self loop is called a asymmetric digraph. For example, V1, V2, V3, V4, almost one directed edge between a pair of vertices. Suppose this is in this direction, this is here, may or may not have a self loop is called a asymmetric digraph. It is not symmetric because there is no edge from, this is from V4 to V1, but there is no edge from V1 to V4. Fine. Now next, complete symmetric digraph. Complete symmetric digraph. A simple digraph in which there is exactly one directed edge, from every vertex to every other vertex. Every vertex to every other vertex is called as complete symmetric digraph. For example, if I will take this one, there will be such a edge. Here it is as such, and here it is as such. This is an example of complete symmetric digraph. Next, complete asymmetric digraph. It is a digraph in which there is exactly one directed edge, between every pair of distinct vertices. There is exactly one edge between every pair of distinct vertices. Okay. For example, as such. Next, balanced digraph. A digraph in which in degree and out degree of each vertex, in degree and out degree of each vertex is same, is called as balanced digraph. Okay, for example, suppose V1, V2, V3. Then here look at what is out degree of V1. Two edges are there, one is away from it, so 1. What about in degree of V1 is also what? 1. What about V2? Is same, 1 out degree, 1 in degree. And what about V3? Is also same one. So for each vertex, if out degree in degree are same, then it is what? Balanced digraph. So this is what? A balanced digraph. It is balanced digraph. Now this is all about the types of digraph. Here in previous video we have seen the types of graph also, that is ordinary graph. Now let's go for the next definition, that is the degree sequence of a graph. Okay. Definition: the degree sequence of a graph is the sequence of the degrees of the vertices of the graph in non-increasing order. In non-increasing order. For example, suppose there is a graph as such with the edges suppose this is A, B, C. Now let me take a loop here. D, E, F, G and H. So first of all, we need to determine the degree of each and every vertex. The degree of the vertices. What are the degrees of vertices? Degree of A, look at here, it is 2, 2 edges are there. Degree of B, this is 2 and loop 2, so 4. Degree of C, how many? 3. Degree of D is what again? 3. Degree of E is 2. Degree of F is how much? 3. Degree of G is 1. And degree of H is isolated, so 0. Therefore, now simply this one we have to arrange in non-increasing means what? Decreasing order. Therefore, the degree sequence of the graph is, what is it? In decreasing order we have to write. So that is descending. So 4, 3 how many times? 1, 2, 3. 3, 3, 3. Okay. Then 2 twice. So 2, 2. Then 1 and what? 0. This is the degree sequence for this. Now another definition is what? Whether the sequence is graphical or not. A sequence D1, D2 and so on up to Dn is called graphical. Is called graphical. If it is the degree sequence of a simple graph G. If it is a degree sequence of a simple graph G. Now how does we can check whether it is graphical or not? There are few steps to check it is graphical or not. So let me give them. Steps to determine whether given degree sequence is graphical. So step 1, it says consider the degree sequence in non-increasing order, means descending. Consider the degree sequence in non-increasing order. Second, if first term is n, that will be a natural number, then reduce next n terms. If it will be a natural number, then reduce the same number of terms by 1, counting from second term. Okay. Third, rearrange the terms. If they are already in descending, then no need to rearrange, but if they are not, then again we need to rearrange the terms in non-increasing order. Fourth step, continue Continue steps 2 and 3. Fifth, if we get all terms 0, the original sequence is graphical. Original sequence is graphical. Otherwise, not graphical. See it carefully. We have to check whether the sequence is graphical or not. First of all, non-increasing order, already we are arranging that. Then first term n belongs to set of natural number. Then reduce the next n terms by 1 counting from second term. If they are not in descending, then rearrange them again. Continue this one again and again till if we get all terms 0, then it is graphical. If it is not, then it is not graphical. Let me take example on this one. Example. Show that the sequence six, 4, 3, 3, 0 is not graphical. Is not graphical. Solution. Given sequence it is 6, 6, 6, 6, 4, 3, 3, 0. Now reduce first 6 terms. First n will be 6, that's why 6 terms by 1 counting from what? Second term. You know that. Counting from second term. So this we will eliminate this one. Simply we have to take this. How many terms? 6 terms. So these many terms we have to reduce. So 5, this one gives 5, 3, 2, 2 and this 0 as it is. Fine. Again, now this is in non-increasing order. So keep it as it is. Again, reduce first how many? 5. 5 terms by counting by 1 counting from again second term. So this is gives 4, 4, 2, 1, 1 and this is 0. 5 terms are these one. Again this is in non-increasing order. So reduce first how many? 4 terms. 4 terms by 1 counting from what? Second term. So this will be 3, 1, 0, 0 and what? 0. Since there exists no simple graph, having one vertex of degree 3 and other of degree 1. Therefore, the given sequence is not graphical. Okay. Now let me give one more example for the same example. Determine whether each of determine whether the given sequence is graphical or not. Graphical or not. If yes, draw graph having the given sequence. Having the given sequence. Suppose the sequence with us 3, 3, 3, 3 and 2. Solution. Given sequence is what? 3, 3, 3, 2. Sorry, one more. Now, first term is 3, so we will reduce these 3 terms by 1 counting from second term. That one, the same. Reduce first 3 terms by 1. Okay, you know that counting from second, so it will be 2, 2, 2 and this 2 as it is. Now this is in non-increasing order. Now again reduce first how many? 2 terms. 2 terms by 1. So it will be 1, 1 and what? 2. Now this is not in non-increasing order, so rearrange in non-increasing order. So what does it use? 2, 1, 1. Now further again reduce for how many? 2 terms. First 2 terms by what? 1. Again from second. We will count from second. Here this one we have been reduced. This one we have to reduce now. What does it gives? 0, 0. So we get 0 here. So since all terms are 0 at the end, so given sequence is what? Graphical. So here what can we say? All terms are 0 at the end. Therefore, given sequence is graphical. Now what is the graph of this one? Now maybe its graph will be, now these are 5 in number, so 5 vertices will be there. Now let me take them as such. Now 4 vertices are of degree 3. Now let me make first of degree 2. Suppose this is of degree 2. Then here we can join these. If I will draw such a graph, look at here, this is degree 3, 3, 3, 3. So this is a graph for it. The graph for given sequence is this one. Okay, so this is about the whether the graph is or the sequence is graphical or not. Now let's see few small examples. Example: is it possible to construct a graph with 12 vertices such that 2 of the vertices have degree 3 and remaining vertices have degree 4. So we will check this whether it is possible or not. So by handshaking lemma, what is with us? Summation of degree of vertices I from what 1 to 12 will be 2 times number of edges, where E is what? Number of edges. Okay. Now according to given, what is given to us? 2 vertices have degree 3. So 2 into what? 3 plus remaining vertices. Remaining are how many? 10 minus 2 will be 10. Remaining vertices have degree what? 4. So 10 into what? 4. That must equal to what? 2 into E. So how many is this? This is 46 equal to 2 into E. So that gives E is equal to what? 23. So this is easily possible to construct a graph with 23 edges and 12 vertices. It is possible to construct a graph with 23 edges and 12 vertices. Okay, which satisfies the given conditions. Another example: is it possible to draw a simple graph with 4 vertices and 7 edges? We have to check this. Solution: in a simple graph, with n vertices, the maximum number of edges, the maximum number of edges are n into n minus 1 upon 2. Okay, hence a simple graph with 4 vertices will have at most 4 into 3 by 2, that is what, 6 edges. Therefore, the graph with 4, a simple graph, therefore the, not a graph, it will be a simple graph. Simple graph with 4 vertices cannot have 7 edges. So given condition should not get satisfied. Such a thing is not possible. Next example. Or let me give as the graph, as a note, graph, number of vertices and number of edges. For standard one, I am giving graph, suppose Kn, Cn, Wn and Kmn. Let me give number of vertices. Are how many here? Obviously n. Here also n vertices. In Wn will be wheel. We are adding one vertex in cycle there. Kmn, here m plus n vertices. M are for V1, n are for V2. Okay. Number of edges. Here number of edges are n into n minus 1 by 2. It is a complete graph. For cycle, the number of edges are n. For this wheel, number of edges will be twice of n. It will be double of it. Okay. Because we will prepare edge there for this vertex from each previous vertex. So it will be twice of it. And here the number of edges are how many? Mn. Okay. Remember this. Now another one. Now the graphs another one more thing, graph and value of n for which it is regular, means the given graph is regular for which value of n. So here the graph I am taking Kn, again complete graph, cycle, then wheel with n vertices and n cubes. So complete graph is regular for n greater equal 1 with degree of each vertex is how much? With degree n minus 1. Okay. Then cycle is regular for n greater equal 3 with degree 2. In cycle, every vertex has degree 2. For wheel, the degree of middle vertex of a wheel will be what? N. That's why it won't be regular, while only Wn is regular only for n is equal to 3. N equal to 3 only. Okay. And W3 is same as, it is same as what? K4. You can check that. Okay. Then this is n cubes. It is regular for n greater equal 1 and with degree n. With degree n. Okay, remember these things. These are two tables you can remember as a for standard things. Okay, now here we will stop for this video. In next video I will take representing graphs and graph isomorphism. Thank you.